Okay, I will go ahead and start. So first of all, thank you everybody who joined the webinar. And this is Gabby O. I am an assistant professor at the University of Utah. And first, I would like to thank the opportunity that DesignSafe to host the webinar, and also thanks Natalie for provide all the assistance that needed. So today's webinar is titled Anatomy of Hybrid Simulation and Real-Time Hybrid Simulation. So it is the first in a series of lectures named Hybrid Simulation 101, and is organized by the Multi-Hazard Engineering Collaboratory on Hybrid Simulation, and also it's called the MECHS. So I would like to spend a little time to explain the MECHS community. So it is a research coordinate network supported by NSF, and you can actually find the website of MECHS under the NHERI community and click MECHS. It will lead you to the website of MECHS on DesignSafe. And it is led by Dr. Shirley Dyke at Purdue University. And the aim of the MECHS coordination network is to facilitate the scientific advances to establish the theory and to expand the capacity for hybrid simulation when it applies to multi-hazard engineering. And currently, it actually has different resources contributed from researchers, developers, and users of hybrid simulation. And you can find all the related resources under the tab of resources on the MECHS website. And this is the overview of the MECHS resource website, and includes the background documents and some reports from the past workshops specific to the hybrid simulation community. And also there are some sample tools and the code and the technical reports and publications contributed by a variety of users and developers. And also, I would like to suggest the learning materials that you can learn. I think currently it's more specific to real-time hybrid simulation. So you can actually have a real-time, virtual real-time simulation running using the real-time platform on Simulink, and a real-time code that's running on your personal PC if you have MATLAB and Simulink and the control toolbox installed. And then also the last one is similar to the previous one, but is focused on the base isolation. So we also encourage and appreciate contribution from the advanced users and other developers. If you have your own material and if you think you can help the community better. So that is the introductory material for the MECHS. And today's presentation is introductory on the hybrid simulation and to hybrid simulation and the real-time hybrid simulation. And it combines the primer that we have on the resource website on the MECHS, and also including two examples of hardware and software setup and the online demo for RTHS example. So I wanted to, before I start the presentation, I want to see if you have the MATLAB installed and then have Simulink and the control toolbox, then you are welcome to go to the MECHS.DesignSafe-CI.org and go to the resources and download the RTHS demo2.zip, which is titled a real-time hybrid simulation demo code. So that is what we are going to use at the end of this presentation. If you have the functionality of the software, and then you are encouraged to walk through the demo with me as well. So that is the introductory part. So this now goes to the outline of the presentation. By the way, if you have any question, you can type in the chat box, and due to the quality of the presentation and to reduce the echoes, I think Natalie muted all the mics of other participants. But if you have questions, I would like to answer it at the end of the presentation. But you can type in through the chat. And also, Joni, if you are there, I would appreciate if you can record and write down or get together the questions they have, and then probably we can answer it in a more compact form. Okay. So I will start the outline, and as I mentioned before, this is introductory to the basic concept of hybrid simulation and real-time hybrid simulation, and I will follow I will follow the format we used in the primer, which we developed in 2014, and talking about the basic concept, basic component used in hybrid simulation, real-time hybrid simulation, and then I found 2 examples for hardware and software configurations, and one specifically for hybrid simulation, another is for real-time hybrid simulation. And just to make everybody aware that actually hybrid simulation and real-time hybrid simulation may have flexible configurations. So what we presented here is to give a better understanding of what we mentioned in the basic components, but you are not really constrained in the use of this example configuration or example setup. Okay, so let's start from the earthquake engineering field. If we are trying to understand the performance of the shear wall structure and the earthquake, and there are multiple ways to do it. First of all, we can do a shake table test, which you can put either a full-scale structure or a scale structure on the shake table, and you can animate one earthquake record or a set of earthquake record, and through sensors and observations you can find out the performance of each component in the shake table test and the global performance. And another way to do it is on the component level. If you only wanted to investigate the shear wall performance under dynamic loading, then you can actually load the shear wall through the loading system or actuators. And then these loadings are typically a predetermined path, either in a triangle shape or a sine wave cyclic shape. And this is named as quasi-static test. And you can investigate the hysteresis behavior and the detail or damage of the tested component and on the component level. And also there are means of computational simulations to investigate different level of response based on what researchers choose to do. And you can investigate the global response by sending the earthquake record to your entire structure simulation, or you can do the same thing as your quasi-static test, just to send a predetermined path to your finite element model of a component. And based on what model you choose to use and what loading path you choose to use, and you can investigate your structure at different levels. But the problem is we can only model the model that we know. So for some complex behavior and some highly nonlinear performance, we usually need to validate the model through using experimental data. And so that leads us to the hybrid and the real-time hybrid simulation. So the concept of hybrid simulation is actually an integration of numerical simulation and physical testing. So if we look at on the right side, if we assume only the shear wall is performed nonlinear during earthquake and the rest of the building is linear, then the equation of motion of the entire or the whole structure can be written in this form. And if we choose to investigate both the component performance and also the performance of the structure with this component in the structure, and then we can use a hybrid simulation with still only choose the shear wall as the component to test, the same as the setup in the quasi-static test. But at this time, what we are using is we have another we have the rest of the building, which is the one that subtract the two shear wall in the numerical substructure. And we decoupled the equation of motion from the right side to the combination of numerical and experiment testing. So the implementation of hybrid simulation is as such. So when you start at the first step of the response, your numerical substructure will calculate the response at the boundary condition and between your numerical substructure and experiment substructure. So I need to emphasize the concept of numerical substructure and experiment substructure, which is the key point of hybrid simulation. So experiment substructure is the test specimen that you have physically set up in your lab. And the numerical substructure normally means the rest of the building that subtract your experiment substructure. So that is the definition of numerical and experiment substructure. So as I mentioned before, so the first step of response will be calculated from your numerical substructure side and sent through your actuator or transfer system to your experiment setup. And due to that motion, due to that displacement, your structure will deform and cause a restoring force according to your displacement. And this measured force will send back to your numerical substructure and include the next step earthquake input and calculate the next step numerical displacement. So basically this loop will run from the first step of your earthquake to the end of your earthquake record to provide the result. Okay. And this is the feedback of the measured force. So the implementation in the lab following this loop is actually you need to have a hydraulic system or loading system. It can be either a hydraulic actuator, and it can be, for example, this test is done in UIC, so they use the loading boundary condition box to implement the boundary condition. So that is another type of loading system. And then we expect the measured force to be recorded at each time step and sent back to our system. So if the assumption we made about the numerical substructure is linear, and if it's valid, then we can make the conclusion that our hybrid simulation should be exact at what we expected, because it should be exact as what we expected in a realistic loading condition. That means if you put the entire structure and loaded with the given earthquake, then the response should be same as the hybrid simulation. And that is because the nonlinear behavior with the shear wall actually is being captured in your hybrid simulation in the physical loading. And then you combine with your numerical substructure response, and then the two add together should be the exact solution for what you expect in reality. And this is the concept of hybrid simulation and the real-time hybrid simulation. So next, I would like to talk about the basic technology and basic components. So when we talk about hybrid simulation versus numerical simulation and experimental method, then we think hybrid simulation and the real-time simulation, they are the same thing. But if we talk inside the hybrid community, actually hybrid simulation and the real-time hybrid simulation, they are slightly different, but they share some basic component in both HS and RTHS. So first of all, both hybrid simulation and the RTHS requires a computational component and a physical component. And in the computational component, it should contain a certain numerical substructure and a time-stepping integration method to solve the equation of motion. And sometimes it requires a coordinator, and basically it's more common in hybrid simulation and not so much in real-time hybrid simulation. And it requires some communication protocol to talk to the physical component. And this may require some certain communication hardware, such like it may be data acquisition board for digital and analog signal conversion, because your computational component is running, providing digital numbers, but your physical component is reading analog, such as voltage, and you need to convert the information between the analog signal to digital signal to allow the communication. And on the physical side, we should have an experiment substructure or several experiment substructures. And that is basically the specimen we would like to test. And a servo-hydraulic system that includes a servo-hydraulic actuator and the servo-hydraulic controller. So you can think of the material test that I think most of you have experienced in the lab. that you use a controller to give command of displacement of your material test machine, that is the loading system, and that controller and that hydraulic actuator, they combine together is what we call the servo hydraulic system. And then the sensors, which we majorly use to measure the feedback, and that feedback can be displacement, which is LVDT sensors, and it also can be force, which is the load cells, and also can be strain gauges, but I rarely see applications using strain gauges for hybrid simulation, but that is, and also accelerometers are type of sensors to provide those feedback. And at the end, to allow the communication between the physical and the computational component, we need to have the compatible combination protocol to send back our measured information to the computational component. So this is the basic template we come up with for hybrid simulation RTHS components. So this here is the configuration of hybrid simulation and real-time hybrid simulation. And as I mentioned before, sometimes the coordinator is involved and sometimes it doesn't. So basically, we take the coordinator and the finite element together as the numerical substructure. So it will provide the experimental displacement. We send it to the experiment substructure, and we have a restoring force measured from the physical lab and set back to the computational part. And the only difference between with coordinator and without coordinator is sometimes if coordinator involves, then it takes the role of time-stepping integration, and then it takes charge, actually also send the displacement to the numerical substructure and have the restore force from the numerical substructure back and calculate the next step response, and then assemble it or disassemble it to a different component. So this is what a coordinator will do. So some actually standard coordinator you may use is like US SimCore or OpenFresco, and you can also find that related information on the MECHS website and the resources. So both actually coordinator and beyond actually are over there. You can take a look. There will be a very flexible setup for numerical part in hybrid simulation. And now when I mean hybrid simulation, I mean it versus real time. So when I don't have the /RTHS, then it means it's only specific to hybrid simulation. So as I mentioned, and the numerical part, it can be using different software such as MATLAB, OpenSys, Abacus, and even ANSYS, and these you can use as a finite element model, and then you can set up in your numerical part. But physical component is more or less more, I think, standard, because you need to start with the communication interface. As I mentioned, you need to send the information back and forth between your physical components and your numerical components. And then in your physical component, you will have the hydraulic system, which I mentioned is the hydraulic controller, such as the MTS controller, which will send your displacement to the hydraulic actuator. And then they will have an internal feedback loop to make sure the displacement you sent is exact as you want as this target displacement. And then after the displacement is sent to your loading system, and then your physical specimen, which is your experiment substructure, will produce a certain restoring force. And that restoring force will go to a data acquisition board that will convert basically a voltage signal to a digital signal, and to send back the digital restoring force to your communication interface and send back to a numerical substructure. And sometimes even in the hybrid simulation, you need the actuator controller. That is because the loading will have some dynamics, and you want to compensate the dynamics of the actuator and also dynamic of your loading paths. And this is a set of actually research topic. So sometimes it will involve additional actuator controller. So to make sure the loading of your numerical displacement is smooth and is as desired to your hydraulic actuator. So there is additional layer involved. And then component in real-time hybrid simulation is slightly different. The reason is the difference between real-time hybrid simulation and hybrid simulation. And the first thing is the real-time hybrid simulation runs 30-second earthquake in 30-second time frame. So it means that everything here you see needs to be run at exactly as the sampling frequency of your simulation. So normally this simulation is run at 1000 Hertz. And that means your time stepping and the numerical substructure model and the actuator controller has to run on a real-time operation system. And normally, I think the two examples I can give as real-time operation system, the first is the Simulink real-time, and also is known as XPC real-time before. And the other one is the LabVIEW real-time, which is the National Instrument product. So these are two examples. And the physical component is more or less the same as hybrid simulation. And the only thing different is you need to have a high-speed data acquisition system and a dynamic actuator, because you are running your experiment in a very high speed in the sampling frequency of 1000 Hertz or above. So you need a high-speed data acquisition. And the dynamic actuator is because the loading you are sending to the actuator is as the frequency of your natural mode of your structure, so that you need your actuator to respond faster. And also, actuator controller is the dominant component in RTHS. It's just because when you run your experiment faster, and then the actuator dynamics is more significant, and that can jeopardize the real-time hybrid simulation performance. So these are the basic components that we come up with in 2014 primer about real-time hybrid simulation and hybrid simulation. So with those conceptual components explained, I would like to use two examples to reflect this terminology to the real examples. And the first one is for hybrid simulation. And this is a report from contributed by Dr. Mosqueda from UCSD, and the test has been implemented in the University of Buffalo at the NHERI lab. And they actually are investigating the collapse of steel moment frame building under seismic loading. And this is a 3-bay, 4-story steel frame, and with the first 1 story and a half and 1 bay and a half as the experiment substructure, and then the rest is their numerical substructure. So you can see the lower is their setup for the experiment substructure, and they have 2 horizontal actuators, 2 vertical actuators to present the response in the seismic response and the gravity frame. And here is their implementation of their experiment. And let's start looking from the right corner, right down corner, which they started to have the numerical simulation, which is representing the numerical substructure. So based on what I read from the report, they use OpenSys and OpenFresco for numerical substructure modeling and for producing the earthquake, for producing the response at boundary condition. And then they send the boundary condition displacement through a PC target that is a real-time operation system for actuator control. And that will convert their desired displacement to a command to the MTS controller. So that is what their servo valve controller. So that is what I mean by if you have the material test and then you have a controller to control the actuator to perform the material test. So this is the controller they use. And this controller will send horizontal command to the 2 horizontal actuator and the vertical command to the 2 vertical actuator to represent the seismic response and the gravity load. And then after the displacement has been imposed, they used the feedback from force from the horizontal actuator load cells, and they calculate the base shear, which is their force feedback, and then they will send to that information will be captured through a data acquisition system, and that response will be sent to the target machine through ScramNet, and they will get together the restoring force and send back to the numerical substructure through TCP/IP protocol. And this part is what they call the three-loop architecture for numerical and experimental information exchange. And you can find that information on the OpenFresco website. OpenFresco is the coordinator they used and is developed by Berkeley. So it is basically is capable of communicating different software, including MATLAB, OpenSys, and others, another simulation platform, and also it can communicate with different hardware through through digital analog signal conversion, and through ScramNet and through TCP/IP. So you can find the manual, which included the examples talking about how actually finite element will talk to the OpenFresco coordinator, and will talk to the controller, which will send the displacement to the server valve control in that example. And that is at the OpenFresco berkeley.edu website. So you can find those information. And in a summary, so this is the list of hardware and software they used in this example. So they used on the computer and to match the format we use. So on the computational component side, they use OpenSys for numerical substructure modeling, and they use OpenFresco for the coordinator. And then the OpenFresco is actually communicate to the PC target, which send the displacement to the actuator and also receive the restoring force from data acquisition system. That is through TCP/IP communication. And on the physical side, they have 4 actuators. 2 are horizontal and 2 are vertical. And each actuator is embedded with the servo valves, LVDT, which is a sensor, and load cell, which measures the force. And then they have the servo valve hydraulic system actuator controller as MTS, STS controller. And they use the PC target, which is an XPC machine that is running MATLAB Simulink in real time with embedded ScramNet card, a PCI ScramNet card for the communication. And they also have a data acquisition board, which is a Pacific Instrument PI660 for measure the force feedback. And the XPC target is communicate with OpenFresco through TCP/IP, and is communicate with MTS, that is for the displacement in ScramNet, and communicate with the data acquisition also in ScramNet, that is for force feedback. So this is the list of the software and hardware for the specific test. And the other examples is for real-time hybrid simulation. And this is my personal research when I was in Purdue University for my PhD. I think I did the test around 2012, and that is implemented at the Harvard Institute of Technology. So the basic test objective for this example is we want to test the MR damper control performance when it is used in a 3-story steel frame. And the MR damper basically is a very high rate dependent device, and it can mitigate the response under dynamic loading. And so we have to use real-time hybrid simulation to investigate its behavior. So the numerical substructure we choose is the 3-story building, and the experimental substructure we choose is the MR damper itself, and it's loaded on the physical setup. So this is the physical setup that we tested at HIT. And the left side is the picture, the right side is the representation of the physical setup. We have an MTS loading frame that is with capacity of 2,500 kilonewton, and it has internal LVDT, and that is the displacement sensor. So for measuring the force, we have a load cell with 15 kilonewton. And then this low MR damper is the experiment substructure. And this loading frame is controlled by the MTS GT controller. So The implementation of the real-time hybrid simulation is because, as I mentioned before, all your numerical substructure, time-stepping method, and actuator control method has to be run on a real-time machine with a real-time operation system. So we are using the DSpace, which is also can be considered as XPC target. So if you read in the previous literature about XPC target, then you know it is the real-time machine that real-time hybrid simulation numerical substructure is running. And now it's changed the name to Simulink real-time, but they are the same thing. So we use a discrete state space to represent the numerical substructure, and we calculate the boundary condition displacement and compensate the structural dynamics through actuator control and send that command to the MTS controller. And then the MTS controller will implement our displacement and measure. We have the force measured through the load cell and send back to our simulation, and through that discrete state space, which is both the numerical simulation of the numerical substructure and also the time stepping. So the list of equipment we used for real-time hybrid simulation, also following the computational and the physical component, is the numerical substructure we modeled with MATLAB Simulink module and this discrete state space MATLAB Simulink module. And we run the component, the computational component on DSpace, which is a real-time machine for Simulink real-time or XPC target. And then we communicate with the physical component through digital signal, the analog signal conversion. And that is for displacement and the force feedback loop. And we used developed actuator controller algorithm we developed in our lab for actuator control, which is the robust integrated actuator controller. So that is the computational component side. And then for the physical component, we have the MTS loading frame, and that is part of the servo hydraulic system. And that is embedded with servo valve and the internal LVET, that is part of the sensors. And we have the MTS Flex GT controller to control the MTS loading frame, and that is also part of the servo hydraulic system. And we have the MR damper, which I didn't list here, which is the experiment substructure. And then we have DSpace 1104 for running the Simulink real-time, and it is embedded with DAQ, data acquisition, with 5 channels, and also it has a 1 ScramNet card. So the ScramNet card, the DSpace is in charge of communicating with the MTS controller through ScramNet, because they have the ScramNet card, and also it communicates with the numerical modeling through the digital analog or the DAQ channels. So that concludes the list of the hardware and software used in a typical real-time hybrid simulation. And I think we probably will run a little bit over time, and I think due to what I confirmed with Natalie, it should be fine time-wise on the conference. But I don't. I will just spend a little, probably 5-6 minutes about the demo code. So the last part is a demonstration of RTHS example. And if you have downloaded the zip file and unzipped the zip file, then you are going to see a list of files with different format showing in your folder. And the main file we are going to run is the M file that write all the variables for this demo code. And then you are going to have a set of .mat file, and that can be the level 1 to 8 is the different compensation for actuator controller, and you have different earthquake record, and you have a mat file for actuator dynamics. And if you open the RTHS DM MDL file, that is the Simulink module, you are going to see represent the real-time hybrid simulation block, I think, it represents real-time hybrid simulation block diagram. And there is a PDF file also associated in the zip file, which give a thorough explanation about what this demo code is about and how each command line in the MATLAB file is representing. So I wanted to briefly talk about the purpose of this demo code. It has 3 layers, and each layer will be a slightly more advanced representation of hybrid simulation or real-time hybrid simulation. So the first layer is simulation of the entire structure. And this entire structure we choose in this model is just 1 degree freedom structure. So basically, the entire structure will run the whole 1 degree freedom structure. And then the second layer is a representation of ideal real-time hybrid simulation. By ideal, we mean we don't have any actuator dynamics involved in the second layer. So we only have numerical substructure and experimental substructure, which is the partition of the mass stiffness damping of the entire structure into 2 parts. One is then we have 1 part for numerical and 1 part for experimental, and we add them together, they should be the entire structure. And the third layer is the realistic representation of a real-time hybrid simulation, which you have your numerical substructure, and you also inside you will have your actuator control algorithm. Okay, I think your actual control algorithm is over here. And the second component is including the actuator control algorithm and the dynamic make of the actuator. So they together can represent the combination of actuator dynamics and the actuator controller in a real-time hybrid simulation. And then the last one represent the experimental substructure of your experimental setup, and that should be the same as the experimental substructure in the ideal RTHS. So the difference between the first one and the second one is the first one is not decoupled, the entire structure is modeled as a whole. The second one, actually your numerical and experimental substructure are separated. And the third one is your numerical substructure and experimental substructure are not only separated, but also actually imposed with actuator controller and actuator dynamics. And that is the basic idea for this numerical simulation. And if you walk through the presentation, you walk through the documentation, then you are going to find out the detailed explanation of how the variable is defined by converting your equation of motion to a second order, from the second order equation of motion to the state space form, which is the idea in control theory. And then you can actually have the exact representation of your equation of motion and the state space. And then you have the partition between your numerical substructure and the experiment substructure, which is derived based on the combination of your experimental mass, numerical mass, experimental damping, numerical damping, experimental stiffness, and numerical stiffness. And then you can decouple the numerical component and the experimental component. And then the last part is, and this part in the code will represent the partitioning and following that derivation. And at the last, you are going to see the actual dynamics representation in the third layer. So I'm not going to talk in detail how the actuator control algorithm is developed, but I wanted to mention this, we have a transfer function that represents the dynamics of the actuator, which is the 4th order transfer function. And then we build a H infinity controller, which can compensate that dynamics. So that is basically explaining this part inside your controller, which is on the second level. It's the second inner level for the third layer. So that is the H infinity controller to compensate your actuator and the actuator dynamics. So I will quickly run through the result. And by the way, if you have a newer version of the MATLAB, when they plot the figure and then the legend, when you download it, it should have something like a (4), and it will give you error when you run the code, because due to the incompatibility of this is the older version and the new MATLAB version. So just delete all the (4) in the legend command, and you should be able to run your code. So after you run the demo code, it will provide you the 5 figures of the response. So the first 3 is, the first figure compares the RTHS, the more advanced RTHS, which is RTHS full case, which we included the actuator dynamics, and the RTHS ideal case, which we only partition the numerical substructure and experiment substructure, and the simulation, which we assume the structure is modeled as a whole. And then that you can see actually this displacement, velocity, and acceleration of your 3 different type of simulation. They are actually matching each other. And in the simulation, in the code, you can actually change the partition ratio between your, I think, your mass, ratio of mass, ratio of stiffness, and then you can run it for different cases. So the first 3 figure will show the comparison between different 3 cases in displacement, acceleration, and velocity. And then the 4th figure will actually show only the 3rd case, which we have a full representation of RTHS, and we have the actuator displacement and the command displacement compared with each other. So the command displacement, what we mean is the displacement we send before we have the actuator controller and before we have actuator dynamics. And then the actuator response is what we have after the actuator. So the idea for actuator control is what we send to the actuator dynamics and the control should be exactly the same as what we compensated. And you can actually try to not having the actuator control loop and just run the command to the actuator dynamics, then you are going to see actually the delay between 2 signals are quite significant. And this figure 4, is just trying to say after we add the compensation method, how is our result looks like. And if you look very closely to the signal, actually they still have a slightly discrepancy, but that discrepancy will not affect much on this certain application. And then the last slides will just figure will just represent the restoring force between the last 2 cases. One is ideal RTHS, which we just partitioned the numerical substructure and experiment substructure without having the actuator dynamics. And one is with actuator dynamics, and then what is the restoring force from the experimental substructure, and what from the simulated experimental substructure. And you can see actually the restoring force will have some discrepancy due to the not perfect controller that we designed for the actuator dynamics. So that with the conclusion using the demo code, I think today you should be able to have a basic understanding about what is hybrid simulation and what is real-time hybrid simulation and what is their difference, and also what is the typical or example setup that hardware and software and not everybody use, but they use in the research field, and also the effect of actuator dynamics and actuator controller in real-time hybrid simulation test. And then at the end, I would to acknowledge the MECHS that is supported by NSF and also DesignSafe for this presentation. And I think I'm running a little bit over time, and I would like to answer questions if we have any from the audience. Okay. So I didn't see any questions from the chat box. I don't know who has something that think I should explain in a more clear way, or have some other suggestions. Okay, then I assume that either everybody is totally understand about what I talked about, or totally lost. But yeah, if you have any questions, you can just email me and or email Joni, whose information is also on the MECHS website. So Joni is a PhD student at Purdue University, and he is in charge of communicating all the between researchers and the coordination network. And if you have questions, okay, okay. I saw actually question from Joni. What do you think next challenge of hybrid simulation RTHS? So that is a slightly bigger question to me as just a junior faculty starting the career. But we have workshops about this MECHS in the research coordination network, and we actually get together a set of suggestions from participants inside and outside the RTHS or hybrid simulation research group. And you actually can take a look on the first MECHS workshop, breaking barriers and building capacity. And we have a very fruitful discussion about what is the common agreement about the challenge in hybrid simulation. I think one of the barriers for hybrid simulation as a community is how to engage other field expertise and the users who don't use hybrid simulation before. And that is one of the reasons we have this webinar going, is because we want to really present the idea of hybrid simulation in a condensed and well easy to understand form to that interest of the outsiders. But internally, I think the development of hybrid simulation, especially I think the challenge is more on the real-time, both in hybrid and real-time hybrid simulation is still at the boundary condition loading. So if we can really reproduce the boundary condition include the shear force and moment and displacement, three all coupled together, if we can control with high degree freedom of actuators and providing exacting the same load to the physical component, I think the result will be more in a higher quality. And also, personally, I'm interested in using hybrid simulation to test the conductors of transmission power. So how to actually represent the boundary condition on the soft material is very interesting to me. So that is also related to the development of real-time and hybrid real-time simulation. Yeah. So the so the research, yeah. So as what I mentioned before, so the discussion and documents of the first MECHS get together is actually be able to download it in the research agenda. So you can click here. So it actually gave the explanation of what the barriers are currently for hybrid simulation. I think that is all I wanted to explain regarding to the next challenges. So any other further questions? If not, I think I would like to thank everybody who participated in the webinar and wish you a great Friday. Yeah. Okay. So then I will stop sharing my screen. Okay, Natalie, do you want to end the meeting like in a more official way, or I should just leave the meeting immediately?
Were there any questions you wanted to answer, or
I think based on what I see on the chat screen, I think I've answered the question, which is the next challenge, but I don't know if there are further questions coming. And I think probably not.
Okay. Well, if there are no more questions, we can go ahead and end it.
Okay, thank you very much, Natalie, for the assistance. And yeah, bye.